84 presents us with an undirected graph that is connected and has no cycles. It's mentioned that this graph starts as a tree. It has n nodes labeled 1 to n, and there's one additional edge. This additional edge causes the tree structure to break. That is, instead of a tree, it ends up creating a cycle somewhere. We have to identify what is this additional edge that breaks the tree structure and return it. So let's do a whiteboard to understand the problem and how we are getting to the solution here. I've copied one example from LeetCode. This is where for this given edges as input, 1,4 is the output, which is 1,4 is the edge which ends up creating a cycle slash breaking the structure representation of a tree. So we'll run through this example. First is 1,2. So we connect 1,2, and in this interconnected set of 1,2, it's a valid tree structure. Then we add 2,3, and this is still valid in the connected set of 1, 2, 3. Finally, we go to 3,4. We connect 3 and 4. It's still a valid structure between 1, 2, 3, and 4. And now finally we get to 1 and 4. The moment we get to 1 and 4, you'll realize that now this is no longer a tree structure. Why? Because 1 was already connected to 4 through 2,3, and connecting 4 and 1 directly ends up creating a cycle. And breaking the overall tree structure where a single node cannot have multiple parents. Now, this is why 1,4 was returned as an output as part of this graph. Now, let's now that is the solution and the problem statement here. Now let's move into figuring out what are the different ways to solve this problem. Now, like most of the graph solutions, DFS and BFS work as a solution here, and the only problem with BFS or DFS solution would be that BFS and DFS work really well when the graph is pre-computed. That is, all edges, nodes are defined, the graph is already there, and we just have to run computations on top of it. The problem here, however, is that we are given edges as a stream of input, which means every time a stream comes, we can run a BFS or DFS, but that would mean against each incoming edge. Like for 1 and 2, we'll run at BFS, DFS, then we'll run it for 2 and 3, then for 3 and 4, 4 and 5, and so on. Which means the overall complexity of using BFS and DFS in their normal fashion would elevate to order of n squared time complexity, which will no longer be an ideal solution for this problem, which can be solved in a linear time using solutions like union find. Now, there are alternative methods of using BFS and DFS where people can construct a graph upfront similar to this by traversing over all the edges and then run a BFS or DFS. The problem in this scenario is that, let's say, even if we compute the graph in order of n and then we run an order of n solution to find the edge creating a cycle or breaking the tree structure, the problem with the solution becomes that because once the graph is created, we have no idea into the rank in which the edges were inserted. So even if BFS or DFS identifies as 3,4 and 1,4 are two edges because of which 4 is now connected to 1 through 2 different paths, it won't be able to tell you should we remove 3,4 to make it a valid tree or should we remove 1,4, which means to run DFS or BFS, within order of n time, we'll have to introduce additional complexities like storing the rank in which the edges were added. Overall, it will make the overall code complexity really high, because of which it's not considered a clean solution for this problem. And there are much cleaner solutions to handle this in a linear time using patterns like union find. So we'll move to union find now. So in general, with union find, we do not really care about the graph or the representation of graphs. We're only worried about the top parents. I'll make it more generic. Whenever you're given an undirected graph with a stream of inputs and you have to figure out structural complexities like cycles being formed, union find is your de facto solution there. And why I mentioned that is, with union find, we don't really care about constructing the entire graph. We are only worried about the representation of parents of each node. By default, we assign each node as their own parent because we have no edges processed right now. Every single node is unique. Rank, which denotes the height, is 0 for all because there's no edge at all. Everyone has no height. Now, how this works is, and remember that going forward, for this example, we are not creating a graph. We're not really worried about the graph visualization for disjoint set unit. We're only worried about how are we representing the parents for each node. So we've processed 1 and 2 as an edge. Now what DSU does is that against both 1 and 2 node for which this edge came into the picture, it will find what their parents are. If their parents are same, that is an indicator that these two edges are already part of the same tree, and creating an edge between these two again will result in a redundant edge or a cycle, which is the structural outlier. And we will visualize it to understand it better. So we get to 1 and 2. We'll check against 1 and 2 what are the parents. For 1 it's 1, for 2 it's 2, meaning they have different parents. That means they're not connected through any graph, any set. So they are disjoint. So at this point of time, 1 and 2 can be connected. When we are connecting 1 and 2, the other aspect of rank comes in. Now ranks is an optimization on top of union find. Union find cares only about the parent. Rank is an optimization to ensure that the height of the representation of the parents is balanced. So worst case solution, if we did not have height and we, let's say, assigned x as the parent, which is 1 is the parent of 2 always, or 2 is the parent of 3, we may end up in a scenario where for unbalanced tree, we will end up in a scenario where we can have a representation close to a linked list or an order of n representation. Versus with the ranks, we will always find the top parent, and the rank of the top parent will be used to assign the smaller graph to the larger graph. So for example, when we are adding 2 or 3 now, instead of adding 2 to 3, parent of 1, which already has a height of, let's say at this point 1, we will attach 3 to 1, which basically makes that instead of a graph where the height increases to 2, we will have a graph where the height remains 1 by connecting 1 to 3 directly, which is basically that we only are interested in tracking the parents and keeping the height of the tree as small as possible. So back to 1 and 2. For 1 and 2, we had assigned them a node. Now, because rank of both 1 and 2 are equal, we don't really care who is the parent of who. For this example, let's assume 1 is the parent of 2. So we'll update the parent of 2 as 1. 1 is already a top parent, so it remains 1. 2 is now pointing to 1 as a parent. Now 2 is a leaf node. We let it height remain 0. 1 is a parent of 2, so the overall height becomes 1 edge. So the max number of edges to leaf node is 1, so the rank becomes 1. Now we get to 2 and 3. When we get to 2 and 3, now we will check against what is the parent of 2 and what is the parent of 3. Now the parent of 2, the top parent of 2 is 1, which is this, and the parent of 3 is 3. So we're technically comparing 1 and 3 at this point, because no, we are not really worried about the graph representation. We are worried about the disjoint set representation of the parent. So now 2 has 1 as the parent, and 1 has a height of 1. 3 has a height of 0. So 3 is a smaller tree representation compared to 1, which has a height of 1. So we assign the smaller representation to the larger one, which means because 1 had a different parent to 3, we accept this relationship. And at the same time, because 1 had a bigger rank compared to 3, we connect 3 to 1 and we say that 3's parent is 1. Similarly, now move to 4. Now we have to connect 3 and 4. So we will find the absolute top of 4. So the parent of 4 is still 4. Parent of 3 is 1. So, and against 1, the rank of 1 is 1 and rank of 4 is 0, which means again, we assign 4 as a node to 1. Finally, we move to the fourth input, which is 1, 4. And yes, this was also 4. So now we move to 1, 4. When we do 1, 4, we see that against 1, the parent is 1. Against 4, the parent is also 1. Now DSU says that because 1 and 4 have the same parent, that means they're already connected, which is also visible in this graph here. Now because these are already connected and we are trying to connect them again, this is a structural outlier. This is how DSU determines that there is a structural inconsistency. That is, there's an additional edge or a cycle getting created, and that is why DSU identifies 1, 4 as an outlier outright and throws 1, 4 as an output of the function. Now this is how DSU works. This is how rank ensures that our height remains log n. If we did not use rank, and let's say we did the solution using DSU without rank, our representation would have been a bit different, where our representation would have been closer to how we use the normal graphs, something like this. So DSU would have still worked, but overall rank wise, the height of the tree would have been very unbalanced, because of which the operations traversing this graph would have been more computationally expensive. And that is why we use ranks, and ranks help us reduce the overall worst case complexity from order of n to order of log n. Now that's a lot to digest, so let's just move into the coding aspect. and we will actually code using exactly what we have done as part of this whiteboard session to get to an ideal code. So this is the boiler template. We've defined the same edge case that we were covering above, and this is our expected output. We have to code the entire implementation. So let's start exactly doing what we did as part of this representation. We defined parents and rank array, which are equal to the overall, whose size are equal to the number of nodes. So first things first, we define parent as an array, we define rank as an array. Now these are equal and their size is equal to the overall number of nodes. So nodes are edges plus 1, so here we do length equal to edges dot length plus 1. Then we instantiate parent to new int length, and we do the same thing for rank. So we have our disjoint set representation using parent and rank based trees height optimization handled using these. Now the next thing to do is initializing them with the default values. So if you remember, by default values we mean we assign each node as their own parent, because initially we assume the graph has no edges, and rank of everyone is 0. So we'll do the same thing here. We assign int I equal to 1, I less than the edge, and I plus yes. So we do parent of I equal to I, and I started with 1 because the LeetCode constraint mentioned that the nodes are ordered from 1 to n. So just to clarify there, and rank of each one is equal to 0. This is our basic initialization done. Now we move to the actual processing. So if you remember, we will process one node at a time. So this was done here, like we process 1 and 2 first, and against 1 and 2 the first thing we do is find their absolute parent. So we'll do the same thing here. We do parent of x. X is our 0th node. So let's say we create a method called find parent. We will define it in a bit. For now, let's assume that this parent will give us the absolute, this method will give us the absolute top parent for any given edge. And similarly, we do parent of y, which would be the edge of 1. Now, the next thing as part of our visualization that we covered was when we have parents for both 1 and 2, if they come out to the same parent, like let's say here for 1 and 4, we found that 1 and 4 both have the same parent 1. We identified that this is a structurally incorrect node. We do the same thing here. So if our parent of x is double equal to parent of y, this is a structural outlier. So we return this edge directly. Let's also add a comment for clarity. Both nodes have common parent, hence redundant cycle detected. Now, what if the parents were different? When the parents were different, we use the rank to determine which node should be assigned as a child to the other node. More generically, the node which had the higher rank was assigned as the parent. So let's do that. So here we will check if the rank of parent of x is greater than the rank of parent of y. This denotes that parent x had a higher height compared to parent y. So parent x should be the parent or the top parent. So we do the same thing. We say that parent x is the top parent. Similarly, we do an else for its inverse, where we say that parent y had the higher rank. So at this point, we make parent y the top parent. And finally, if both had the same rank, which was the case of our initial input when 1 also was 0, we assign either one of them as the top parent, and against that, we will just increment the rank by 1 to denote the additional edge that was added. So this would mean that we can do really anything here. For our case, let's say we assign parent of y equal to parent of x, and because now parent of x has added this new edge to parent y, and initially the rank were equal, so the rank would increase by 1. So rank of parent of x plus plus. This is equivalent to how rank 1 was 0 and rank 2 was 0, and when we added both of these and made 1 the parent, we appended or incremented the rank by 1 to denote this additional edge that was added. This is not needed in the future iterations, because whenever 1 was added to 3 or 4, its height was already 1, which was basically already covered by this edge, so we did not need any other edge there. So yeah, this is our in main code section. We'll also cover this case. This is basically when we have no cycle detected, written no h or yeah, written no h. So this covers the main method. Now we have to cover find parent. Find parent is basically will return a integer which would be the absolute top parent it could find for any given node, which means when I do a find parent of 4, we do a recursive logic saying that parent of 4 is 1, then we call parent of 4, parent of 1, parent 1 let's say had a parent of 0, then it would return 0 and so on. So for this one, what we do is that we define a closing condition which basically says that if my parent of node is double equal to node, that is if I am the top parent, I will return myself immediately. This is top parent, no other parent. So there's no point to continue the recursion logic forward. We'll return it as it is. Otherwise, we will return the parent of the current node, which is this. So now this, to be specific, is path compression, which basically helps you mitigate the worst time complexity from order of n to order of log n. And what that basically means is that let's assume we had a couple of dependencies here. One was pointing to 0 as well. When we find the rank of 4, it was initially 1. Let's say 1 also had another parent of 0. So in the return path, when 0 as an output comes to this recursion call, which was for 1, we assign 0 as the parent of 1. Similarly, we return 0 again, and for 4 also we update 0 as the parent, so that the next time I call find parent of 4, it directly returns me 0 instead of 1, which basically compresses the amount of traversals that I have to do and improves the overall complexity, helps with the overall complexity. So this is the high level solution. We save it and let's run it. So we get 1 and 4 as the output, which is as expected, and the second part of our solution, or the second example, was this. So yeah, this is already covered there. Let's remove this. So let's save it and let's run it. So yeah, we get 2 and 3 as output. So the solution is working fine as expected. Now on to the overall complexity of the solution. We were compressing the path, and at the same time the rank ensures that we are in a log n state. The overall time complexity is an amortized order of n, alpha n, which basically for all practical reasons is order of n itself, because as you will see here, the height does not really grow for any set of valid constraints to any rank greater than 3 or 4, and that's why it's an order of n solution for most part of it. So that was the ideal solution for LeetCode problem 684. Thank you.